Okay, I'll share the screen. Okay, can you see the screen? Is it visible for everyone? Okay. Okay, all right. So last time we were doing the waves and oscillations, right? And we talked about simple harmonic motion, and that's actually the motion that we'll be concerned with in this entire chapter. So we talked about, well, what is the differential equation? How does the differential equation apply in our case? I showed you how Newton's second law is just really a linear differential equation. And from that, we talked about this thing that is an acceleration, and how can I write down an expression for the force, the restoring force of something that is oscillating, right? So for example, if I consider again a pendulum, let me draw something like this. And now the mean position is this vertical line for this pendulum to rest at. And the restoring force of this oscillation is, which is to the center of, or towards the mean position, right? And that restoring force is given by this expression. And the negative sign is just telling you that the force is directed towards the center instead of outside, where I pulled the bob outside, right? So the negative sign shows that the force is in the opposite direction of where I pulled the bob, which is inwards to the center of the to the mean position, right? So you can also think about it in terms of a something that is called a simple harmonic oscillator. And in fact, this is the system that we'll be very closely working with. It is, in fact, the simplest mechanical system whose motion follows this linear differential equation. And it has these coefficients, which you can see this m mass and the oscillation frequency. These are some of the constant coefficients. And so we have multiple examples of this thing, right? I mean, you can consider a simple harmonic oscillator that is horizontally on some surface. So here we have some spring that is attached to any mass, right? M mass. The spring, the geometrical and the materialistic nature of the spring defines the spring constant K, right? So now imagine that if this mass was resting in this position and I were to displace it some distance x from its mean position and then leave it, then because there is a spring, it's going to oscillate in this way, right? Back and forth until and unless it eventually comes to a stop at its mean position. All right, so this is a simple harmonic oscillator, and you can write down the equation for force for this thing as well, which is F is equal to, now the restoring force for such an oscillator is minus K times X, where I have already told you that K is a spring constant, and it's a constant, right? And it depends on the type of the spring that we are using. X is the displacement from mean position, right? So if I displace it and I know how much I've displaced the block, and I know what kind of a spring that I'm using, then I can compute the force with which this mass M will be directed back to its mean position, right? So this is that force. It's also called the restoring force. All right, so is this clear? Is the idea clear? Can you please unmute yourself and let me know if you're following along? Is there any question? Alicia, Hasib, Omar, Anna.
Yes, sir.
Okay. Are you following along? Is there any question? Are you getting it?
Yes, sir.
So you understand what's a simple harmonic oscillator?
Yeah.
Do you understand these equations?
Yes.
You do? All right. So, well, again, if I'm saying that it's really just an oscillator so far, but if I say that it is a simple harmonic oscillator, then as we discussed in the previous class, it should be following the simple harmonic motion. And what were the two conditions for simple harmonic motion? The first one is for any oscillatory motion that it's a periodic oscillations or periodic motion, right? Now, second condition, which is the most important one for simple harmonic motion, and that is that the acceleration, which is directed towards the center to the mean position, is proportional to the displacement, right? So the acceleration is proportional to the negative of displacement. Negative sign is again ensuring that it's towards the mean position, right? And here from here we develop this equation that A is equal to minus some constant times X. It just turns out that this constant is the square of the angular frequency of the oscillations. I'm sure you must be familiar with this thing, that this angular frequency is just defined as a frequency multiplied by 2 pi. 2 pi ensures one cycle, right? So 2 pi is, this is in radians, 2 pi radians, and that's just 360 degrees, which if you're familiar with is just the complete revolution, right? So one cycle, so that's why we multiply a factor of 2 pi with this frequency to get an angular frequency for one complete revolution. If you're further familiar with the fact that the frequency is defined as 1 over the time period, where I'm sure that you know that time period is the time that it takes for one oscillation to take place. One oscillation is, for example, for this bob, if I move it here, then it's going to come to its mean position, then it's going to rise some height over here, and then it's going to come back to its mean position, and then it's going to rise some height over here. Now, this thing is one oscillation, right? So this thing is one oscillation. And that's the time it takes for this to happen is the time period, and this is f. So I can write down this angular frequency as 2 pi divided by the time period of the oscillation as well. All right. So that's your simple harmonic motion. And these are the very main conditions for a simple harmonic motion to take place, right? Now, we know I'm going to describe some of the graphs very quickly for displacement, velocity, and acceleration. So let's see how these graphs look like. Displacement, velocity, and acceleration. All right. So of course, these graphs will be drawn considering the fact that we're talking about a periodic motion, and we'll use some of the mathematics, help from mathematics, really, to have a function that is periodic. In mathematics, what type of functions are periodic? Can anyone answer this question? Can you unmute yourself and answer? Is anyone familiar with what are periodic functions in mathematics? Functions like, let me write over here. Periodic functions are functions like a cosine, sine, right? And then you can have these hyperbolics and then square of these functions, and you can make a lot of functions out of these two functions, really, right? So even in fact, the tangent function is made out of these functions, which is sine by cos, right? Now, it turns out that mathematicians have already developed the mathematics that we needed to study vibratory motion. And this is the trigonometry is that mathematics. And so we'll use that to understand these harmonic oscillations, right? So for example, suppose your solution can be either cos or sine, right? So suppose that I have I have a system of an oscillator or any periodic motion, then I'll have a displacement time graph for that motion. Let's say displacement is represented with x, t is time. We know when an oscillation happens, I'll draw the figure over here as well for you. We know initially what happens normally is that something is resting in its mean position. So it will be on this dotted line really before. Then you move it. So what you're doing is you're increasing the displacement. And then what happens is that the displacements, this distance x starts to decrease when it comes back towards its mean position. Eventually, it comes to 0 when it's at its mean position. It's x is equal to 0 over here, right? X is 0 over here, and x is some maximum value x naught over here, right? So this maximum value is some value x naught. I'll just call it. It's just a number. It's the maximum displacement that I can give to this bob. And then it starts decreasing, right? First it ris, and then now it's decreasing. It's going to fall to 0. When it's at 0, physically the pendulum is over here right now when it's at 0, and then it's going to increase in the other direction, right? So it's going to rise over here. So that's why the displacement becomes negative, and then it comes back again. When it rises over here, then it's going to come back, and eventually it's going to also come back to this mean position. So it's going to go to 0 again. And when it's at this point, this is minus the same number x naught. Minus just tells you that it is on the opposite side. So it's the opposite extreme position of the bob, right? And then it falls to 0. Here it's at its mean position. So this is just one complete oscillation. Multiple of these will happen, and finally, eventually, it will come to a stop. So you can repeat this graph over and over and over again. And so you get something like this, and then it keeps on repeating itself, right? So this is the displacement versus time. Is this clear? Is the displacement versus time graph clear for an oscillation?
Yes.
It's clear. Okay. All right. So we know that if I want to draw a velocity time graph, so I'll just velocity time graph. We know velocity is just displacement over time. Or in other words, I can write the same thing as it is the gradient of displacement time graph, right? Because the gradient of displacement time would be x, change in x divided by change in time, right? That's the gradient of a displacement time graph. That's the definition of how you find a gradient of any curve or a slope. And so that's, we're going to use this technique that the gradient of a displacement time graph will give you a velocity time graph. So now it's very simple to draw a velocity time graph corresponding to this displacement. So I can see now how did the velocity changed with time, right? So here we have these axes. Let me just try to draw it like this so that we have everything synchronized. This is the velocity and this is time. Now let's see. Uh, Initially, we know that if I raised this pendulum, this bob, and then I release it, it's going to have the highest possible velocity uh, when it is at the center. And then it's going to rise again. And why do I say that? If you're familiar with the conservation of energies, then you know then when the bob is at raised at some height, right? At some height, it's raised. At this point, it has the maximum of potential energy. And then when its height is minimum, that's when it have, which is over here at the mean position, that's when it have the maximum kinetic energy, right? So when it's at the center, when it's crossing the center, it has the maximum speed, right? So the velocity starts as a maximum. So you can, I'll tell you this technique by looking at the graph and looking at the physical situation and then drawing the graph. And then I'll tell you a very simple technique in which you can draw a velocity time graph from a displacement time graph. So by looking at the physics of what's happening, the as I've told you that at the center, when time is 0, t equals 0 is at the center mean position, the kinetic energy is the maximum, meaning the velocity of the bob is the maximum. And then eventually, as it raises to a height, the kinetic energy starts to fall, but the potential energy starts to rise. So when the potential energy rises, the velocity becomes smaller and smaller, smaller and smaller, and eventually it drops to 0. And then again, when it's at when the velocity is at 0, it is at a particular height, right? So for example, it's over here. At this point, the kinetic energy is minimum, so velocity is minimum. But now it's going to change its direction and start oscillating in this direction. So again, the velocity starts increasing, 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 and it becomes a maximum at some point in the opposite direction. That's why it's a negative number over here, right? And then you can continue the same thing like this and so on, right? So ignore the neatness of the graph, but hopefully is the idea clear? How did I drew the velocity time graph and the displacement time graph?
Yes.
Clear? Or all right. So understanding the displacement time graph is the most important, because now if you uh, use a trick borrowed from mathematics, you can just draw a velocity time graph instantly, because as I said that the gradient of a displacement time graph is a velocity time graph. Gradient is yes, exactly, Hasib. So if the displacement time graph is a sine curve, then the then the velocity time graph would be the cos curve. And the reason for that is what I'm getting into right now, because I have defined velocity time graph as the gradient of the displacement time graph, which is how it is. We know that if we talked slightly about derivatives, and last time I understood that there are some people who do not take mathematics. And so derivative essentially is the time derivative, as I explained. So for a displacement, if I say delta x by delta t, then loosely speaking, I can say that this is derivative of x with respect to time, right? We do an entire thing. We say that we make this delta t interval so small, and that's when it converts into a derivative operator. But for now, you can say that anything that looks like this can be written as a derivative dx by dt, like this. If that's the case, then if I have a sine function, right, the derivative d by dx or d by dt of this thing is a cos function. And if I have a cos function, then a derivative of this thing is a minus sine function, right? So if you remember this thing, then if I have a displacement graph, which looks like, I'm going to draw a cos function now, which looks like this. And then the velocity time graph will be a sine function, but with a negative signature. So it will look something like this, right? So this is the negative sine function. So this is the velocity time graph. So all you did was you understood what derivatives are, right? And so the derivative of the sine function, because derivative behaves like a gradient, right? It is a gradient, really. So the gradient of a sine function, which is displacement, maybe, is cos function, which would then be the velocity. And if the displacement is a cos function, then the gradient of that thing, which is a derivative, would be a minus sine function. And then drawing this graph is essentially very simple. The velocity time graph is very simple to draw by just knowing which function is which, right? So we know that minus sign looks like this. Okay, so is that clear? Is it clear?
Yes, sir.
Okay, all right. So good. Now the final thing for these graphs, one of the graphs that's left, is the acceleration time graph. And it's the simplest one, simply because of the fact that, remember, that acceleration was minus omega squared x. This thing is a constant. We can ignore it for now while we're drawing graphs. Multiplying a constant with something just changes its amplitude, right? But does not change the shape of the graph, really. And because we see that a is the same as x, right? The same meaning it's proportional to x, right? So a is proportional to actually minus x, right? So if I have a displacement time graph that looks something like something like this. Sorry, this is a displacement time graph. Suppose it looks something like this, right? Then the acceleration time graph should look a flipped version of this thing, right? Because of this negative sign, the maximum amplitude becomes the minimum amplitude. So it will look something like this, where it have now become a negative sign, right? And then the minimum becomes the maximum, like this. But the shape stays the same as of the displacement time graph, because it is just proportional to this thing, right? So if x was a sine function, then the acceleration time graph will also remain a sine function, but just flipped upside down due to this negative signature. Similarly, if it were a cos function that looked something like this, displacement time was a cos function, then the acceleration time corresponding to this one would be a negative cos function. So if it's starting at maximum over here, now an acceleration would start at a minimum and it would look something like this. So the minimum of this thing would be the maximum in the acceleration, like this. And then again, the maximum in displacement time would be a minimum in the acceleration time graph. So is that clear?
Yes.
So this thing corresponds to this point. This one corresponds to this point, while this one corresponds to this point. All right. So so far, all of these graphs, are they clear? Displacement, acceleration, and time. Sorry, displacement, velocity, and acceleration graphs. All right. So okay, so now we can talk about, are you familiar with the idea of amplitudes of oscillations? Amplitude of an oscillation could be, it is the maximum value of any of these quantities. So for example, if you're talking about a displacement, the amplitude of this oscillation is the maximum value that the displacement can have. So this is defined as the amplitude of the displacement time graph, or the oscillation that is happening, right? Okay, so uh, we can talk now even about this thing. It's energies of a simple harmonic motion, right? You're also familiar with a work energy thing, where we also see that we can relate energy with force. And so now we'll use that thing to understand energy and simple harmonic motion, right? All right. Uh, I think before I come to this thing, or I guess we can start with this. Okay, so of course we know that when we have an oscillatory motion, right? So suppose you have a bob again, and it's oscillating. There is this exchange of kinetic potential, then from potential to kinetic, and then again from kinetic to potential. As in here we have maximum potential, here we have maximum kinetic, and then when it comes to this height, we have again maximum potential. And then as the oscillations happen, this transfer of continuous transfer of energy keeps happening, right? So now the you can say the important point is, again, one of the most important principles of physics. It is conservation of energy. That yes, of course, this transfer of energy happens, but the total energy is conserved, right? It is a constant, it does not change. The total energy of our system does not change, right? So if I take the potential energy and the kinetic energy, the sum of this will be a constant number, right? And this number will not change. So if I were to draw the kinetic energy of my oscillations with respect to the position of the system, right? So here I have kinetic energy, and here I have the position of this system. I've already discussed this thing that at the center we have maximum kinetic energy. So when the object is at its zero displacement, it's going to have a maximum value of kinetic energy. And as it oscillates, it is going to drop its kinetic energy and eventually come to zero at the maximum displacement, where the potential energy is now maximum. So this thing will look something like this. And the same thing happens on this opposite side as well, right? So when it comes back to its center, it again becomes maximum. And then on the opposite side, it reaches its maximum position, where the potential energy again drops, the kinetic energy drops to zero, right? So this is some positive x naught, and this is some minus x naught being the amplitude of the oscillation. So is that clear? Is this energy, kinetic energy versus displacement clear? Why does the shape of the graph look like this? That's the thing that you should be understanding right now. Comparing it with the physical situation that's happening. So is that clear?
Yes, sir.
Okay, all right. So now I want you, all of you, or anyone volunteer, to tell me that how should I expect the potential energy graph with respect to displacement. I'll give you a hint that it's either the kinetic energy or the potential energy. It's an exchange between the two, right?
Sir,
So
opposite to the kinetic energy?
Opposite to the kinetic energy. So you're saying that when the kinetic energy is maximum, then at that point, the potential energy should be a minimum value. And when the kinetic energy is the minimum, then the potential energy should be a maximum value. So it would look something like this. But the same thing is happening on the other extreme position. So we'll draw a mirror image, something like this. So it's a parabola like this, where this thing corresponds to a one mean maximum extreme position, while this corresponds to the opposite extreme position, right? So that's is that clear for everyone? Does everyone understand why is this graph the opposite of the kinetic energy graph?
Yes, sir.
Okay, good. So now remembering the conservation of energy, uh, how should the total energy graph look like? Here, let's suppose that I'm writing the total energy, and here is the position. I write down the conservation of energy, that the total energy is the sum of kinetic and potential energy, which is a constant, right? So how should that look if I draw it against the mean position? Suppose here is the maximum and here is the minimum. Anyone? It should be a constant number, right? So suppose the total energy will obviously be greater than zero. That's clear to everyone, right? The total energy of the system will not be zero.